Section 6.1, Development of the Modern Periodic Table. Some objectives of this lesson are trace the development of the periodic table and identify key features of the periodic table. Some vocabulary review is atomic number, and some new vocabulary you'll come across is periodic law, group, period, representative element, transition element, metal, alkali metal, alkaline earth metal, transition metal, intertransition metal, lanthanide series, actinide series, nonmetal, halogen, noble gas, and metalloid. So in the late 1700s, French scientist Lavoisier compiled a list of the known elements at that time. And there was only about 33 elements at this given time, and he put them into 4 categories. Many of these elements, such as silver, gold, carbon, and oxygen, have been known since prehistoric times. The 1800s brought a large increase in the number of known elements. The advent of electricity, which was used to break down compounds into their components, and the development of the spectrometer, which was used to identify the newly isolated elements, played a major role in the advancement of chemistry. The Industrial Revolution of the mid-1800s also played a major role, which led to the development of many new chemistry-based industries, such as the manufacture of petrochemicals, soaps, dyes, as well as fertilizers. By 1870, there were approximately 70 known elements. Along with the discovery of new elements came volumes of new scientific data related to the elements and their compounds. Chemists of the time were overwhelmed with learning the properties of so many new elements and compounds. What chemists needed was a tool for organizing the many facts associated with the elements. A significant step towards this goal came in 1860 when chemists agreed upon a method for accurately determining the atomic mass of the element. Until this time, different chemists used different mass values in their work, making the results of one chemist's work hard to reproduce by another. With newly agreed upon atomic masses for the elements, the search for relationships between atomic mass and elemental properties and a way to organize the elements became in earnest. In 1864, English chemist John Newlands proposed and organized schemes for the elements. He noticed that elements were arranged by increasing atomic mass, their properties repeated every 8th element. A pattern such as this is called periodic because it repeats in a specific manner. Newlands named the periodic relationship that he observed in chemical properties the law of octaves, after the musical octave in which each note repeats every 8th tone. And we can see over here, this was what John Newlands' periodic table looked like, right? Hydrogen to fluorine, then we skip another row, right? Or we would say we'd skip an octave, from lithium to sodium, so on and so forth. I guess this is maybe gallium to magnesium. I guess in time, right, some of these symbols started to change. I digress. All right. So in this figure, right, it shows how Newlands organized 14 of the elements known in the mid-1860s. Acceptance of the law of octaves was hampered because the law did not work for all of the known elements. Also, the use of the word octave was harshly criticized by fellow scientists, who thought that the musical analogy was unscientific. While his law was not generally accepted, the passage of a few years would show that Newlands was basically correct. The properties of elements do repeat in a periodic way. In 1869, German chemist Meyer and Russian chemist Mendeleev each demonstrated a connection between atomic mass and elemental properties. Mendeleev, however, is generally given more credit than Meyer because he published his organizational scheme first. Like Newlands several years earlier, Mendeleev noticed that when the elements were ordered by increasing atomic mass, there was a periodic pattern in their properties. By arranging the elements in order of increasing atomic mass into columns with similar properties, Mendeleev organized the elements into a periodic table. Mendeleev's table, shown below, became widely accepted because he predicted the existence and properties of undiscovered elements that were later found. Mendeleev left blanks in the table where he thought the undiscovered elements should go. By noting trends in the properties of known elements, he was able to predict the properties of the yet-to-be-discovered elements, scandium, gallium, and germanium. Right? If you kind of look at this table over here, right, you can see that he's leaving these blanks as he's going. And again, after them, you have these dashes. And again, that's with the blanks in which he was referring to. Mendeleev's table, however, was not completely correct. After several new elements were discovered and the atomic masses of the known elements were more accurately determined, it became apparent that several elements in his table were not in the correct order. Arranging the elements by mass resulted in several elements being placed in groups of elements with different properties. The reason for this problem was determined by in 1913 by an English chemist, Moseley. As you might recall from Chapter 4, Moseley discovered that atoms of each element contain a unique number of protons in their nuclei, the number of protons being equal to the atom's atomic number. By arranging the elements in order of increasing atomic number, the problem with the order of the elements in the periodic table were solved. Moseley's arrangement of elements by atomic number resulted in a clear periodic pattern of properties. And the statement that there is a periodic repetition of chemical and physical properties of the elements when they are arranged by increasing atomic number is called the periodic law. Mendeleev, 6.2 summarizes the contributions of Newland and Meyer, Mendeleev, and Moseley to the development of the periodic table. The periodic table brought order to seemingly unrelated facts and became a significant tool for chemists. It is useful reference for understanding and predicting the properties of elements and for organizing knowledge of atomic structure. Again, here's just a little breakdown on table 6.2 of the contributions that these scientists brought forward. Right, from Newlands to Meyer to Mendeleev, all the way to Moseley. The modern periodic table consists of boxes, each containing an element name, symbol, atomic number, and atomic mass. A typical box from the table shown at right. The boxes are arranged in order of increasing atomic number into a series of columns called groups or families, and rows which we call periods. The table on the next page, right, in your textbook gives you an idea of what the periodic table was. For a more up-to-date periodic table, I like to go ahead and use ptable.com. Kind of gives you a better idea, and it's a little more interactive as well. But if we go ahead and look at this figure 6.3, a typical box from the periodic table will go ahead and give you the element's name. It'll also go ahead and give you the symbol. It'll give you the atomic number, as well as the mass. Beginning with hydrogen in period 1, there are a total of 7 periods. Each group is numbered 1 through 18. For example, period 4 contains potassium and calcium. Scandium is in the third column from the left, which is group 3. Oxygen is in group 16. The elements in groups 1, 2, and 13 to 18 possess a wide range of chemical and physical properties. For this reason, they are often referred to as the main group or representative elements. The elements in groups 3 to 12 are referred to as transition elements. Elements are classified as metals, nonmetals, and metalloids. Let me just give you an idea. Give you an idea of the periodic table, right? Here we have, right, groups 1 to 2, and then if we jump across, we got 13, 14, 15, 16, and 17, right? These are known as your representative elements, whereas these elements in the middle, your D block elements, are known as your transition elements. Right? And again, I like using this P table because it gives you an idea, a better idea of what we have. And again, it's more up to date with the newly discovered elements as well. Right. Elements that are generally shiny when smooth and clean, solid at room temperature, and good conductors of heat and electricity are called metals. Most metals are also malleable and ductile, meaning that they can be pounded into thin sheets and drawn into wires, respectively. Most representative elements and all transition elements are metals. If you look at boron in column 13, you will see a heavy stair-step line that zigs down to astatine at the bottom of group 17. This stair-step line is a visual divider between the metals and the nonmetals on the table. And again, just to kind of show you, right, that stair-step from boron to silicon to arsenic all the way down to astatine, right, are called your metalloids. So anything with that little M, right, boron, silicon, germanium, arsenic, antimony, tellurium, and astatine, right, it's a little staircase. Those are what separates your metals from your nonmetals. And in that, we call those elements your metalloids. Alkali metals, except for hydrogen, all the elements on the left side of the table are metals. The group 1 elements, again except for hydrogen, are known as the alkali metals. Because they are so reactive, alkali metals usually exist as a compound with other elements. Two familiar alkali metals are sodium, one of the components of salt, and lithium, which are often used in batteries. The alkaline earth metals are in group 2. They are also highly reactive. Calcium and magnesium, two minerals important for your health, are examples of alkaline earth metals. Because magnesium is sold and relatively light, it is used in the fabrication of electronic devices such as laptops. The transition elements are divided into transition metals and intertransition metals. The two sets of intertransition metals are known as the lanthanide series and actinide series and are located along the bottom of the periodic table. Just to show you, if we were to go ahead and look at the periodic table, right, these are your lanthanide and actinide series, right, starting with lanthanum and actinium, right, all the way down here, right, or also known as your F block elements, right, and up here, right, these D block elements are what we call your transition metals. So these are your transition metals, right, and then these are known as your intertransition metals. Now, the rest of the elements in group 3 to 12 make up the transition metals. Elements from the lanthanide series are used extensively as phosphors, substances that emit light when struck by electrons. Because it is strong and light, the transition metal titanium is used to make frames for bicycles and eyeglasses. Nonmetals occupy the upper right side of the periodic table. Right, so in the upper right, everything labeled with a little N are called your nonmetals. Carbon, nitrogen, oxygen, fluorine, phosphorus, sulfur, chlorine, selenium, bromine, and iodine are all known as your nonmetals. As well as helium, neon, argon, krypton, xenon, and radon. Nonmetals are elements that are generally gases or brittle, dull-looking solids. They are poor conductors of heat and electricity. The only nonmetal that is a liquid at room temperature is bromine. The most abundant element in the human body is the nonmetal oxygen, which constitutes 65% of the body mass. Group 17 elements is composed of highly reactive elements that are known as halogens. Like the group 1 and group 2 elements, the halogens are often part of compounds. Compounds made with the halogen fluorine are commonly added to toothpaste and drinking water to prevent tooth decay. The extremely unreactive group 18 elements are commonly called the noble gases, and they could be used in those neon light-up signs. The elements in the green boxes bordering the stair step in the periodic table provided by the textbook are known as your metalloids or your semi-metals. Metalloids have physical and chemical properties of both metals and non-metals. Silicon and germanium are two important metalloids used extensively in computer chips and solar cells. Silicon is also used to make prosthetics or in lifelike applications. This introduction to the periodic table touches only the surface of its usefulness. You can refer to the Elements Handbook at the end of your textbook to learn more about the elements in the various groups. A section summary of 6.1. The elements were first organized by increasing atomic mass, which led to inconsistencies. Later, they were organized by increasing atomic number. The periodic law states that when the elements are arranged by increasing atomic number, there is a periodic repetition of their chemical and physical properties. The periodic table organizes the elements into periods, or rows, and groups, which are your columns. And again, groups could also be called families. Elements with similar properties are in the same group. Or you can also say elements in the same properties, elements with the similar properties are in the same family. Elements are classified as either metals, nonmetals, or metalloids.